Hello, my name is Caleb Crenshaw, and this is the Physics 2211 Lab 1, utilizing Newton's second law to compare experimental and expected data. So, in the introduction, we're utilizing Newton's second law, and with this in mind, we're utilizing the equations, the velocity update formula, and the uh, position update formula. So, final velocity is equal to initial velocity plus a, which can be broken down to net force divided by mass times change in t. With the assumption that velocity is constant, we can assume the net force is zero. This leaves us with final velocity is equal to the initial velocity plus zero times t, which is equal to the initial velocity. This is the velocity update formula, and in this case is used to determine the velocity after a given amount of force is utilized, which in this case is zero. For the position, we can use the equation final position is equal to initial position plus initial velocity times t. Typically, you have the plus 1/2 a t squared, but because a is equal to zero, the rest of that is canceled out. So in Tracker, this is how the data was collected. The ball started at the initial point 0, which can be seen all the way to the left, and then that's where the axis is, or the origin. Obviously, there's a little bit of offset because of the fact that I could not get the mouse to click straight over the axis, so that's why the the initial is 0.00696 instead of 0, or the initial position. So at each frame, it was broken up into each frame. So every 0.033, which is one frame, after using a 30 frame per second camera, after each frame, I clicked or tried to click the center of the ball to get the changed position, which would then be recorded, and I can put that into the data on Excel. So in the data from Excel, I got from Tracker, I was able to use the average velocity equation from the first 2 points, which is one frame, or the average velocity from the first or the zero frame, and then from the frame immediately after that. So from time equals or t equals 0 to time t equals 0.033, which is one frame, you have 0.0313 minus negative 0.00696 divided by 0.0333 minus 0, which is again one frame. This gives me the average velocity of 1.148 meters per second. So this is the initial starting velocity. In the data analysis, you see that the experimental versus expected is a little bit different. The expected was gotten by multiplying the average velocity by each time interval. So after every 0.033 seconds, it was multiplied by the 1.148 velocity. So you get a very linear line, which is again to be expected, and you have the experimental line. You might be wondering why is there a little bit of difference. There's a number of reasons. So for one, we know that the testers that the velocity is not actually constant. Due to forces such as friction, we have a small amount of negative force in the ball at all rolling times. This gives us a slight change in A, which gives us a slight change in the velocity. This means that the net force is not actually zero, leaving for a small acceleration. Centering the marker on the mass leaves for experimental error as well. It's almost impossible for me to directly put the mouse every time at the center of the ball, leaving perfect distances between the ball at one frame and the ball at another. So for improvement, I could do something where you use the average velocity from the end of the experimental data and at the beginning, and this will give you a much closer graph. But there will probably be differences in the center due to the friction that was mentioned. So in this simulation slide, you have all the data on the left side. So the mass of the ball is 0.624. This isn't used, however, because of the assumed net force of zero. So you have the position vector at 0, which is the origin, the velocity of the ball at 1.148 meters per second in the x direction, and then the step size being 0.033 seconds, which is one frame. So while t is less than 1.533, which is the end of all the frames or the final seconds, you have the F net vector equal to 0, because there's no acting forces, supposedly. The ball velocity stays the same because the F net is 0, so it cancels out that whole second term. So you have ball velocity is equal to ball velocity. The position of the ball is equal to the position of the ball plus the ball velocity times the step size. So this will keep increasing and you'll keep getting new data points. The t changes by the step size, so t is increasing by 0.033, which is again one frame. So on the right side, we can see that the yellow dot's the origin, and then the blue mass is the basketball after it rolled in the positive x direction. Thank you again.